This is page 4 of the memory allocation notes. So the details about how malloc works are a little bit heavy, maybe a little ambiguous, the way I showed them to you. But now we can talk with a bit of understanding about it, about what kind of things you can mess up when you're using pointers. So let's call this pointer mistakes that we, the programmers, can make. And one pretty easy one to do is just straight up lose the pointer. So you might, call malloc, you get an address back, you do something with it, and then your pointer to that block just goes out of scope, and that variable, you no longer have a variable with the address of the block, so you've lost an allocated block. So losing pointers to allocated blocks. And this is a memory leak, and they're very common. Well, for example, I've been running a web app that uses the Tomcat Java server. It's an Apache tool, and the memory leaks aren't as bad as they used to be, but it's still there. It's a big complex program. Okay, and now I'm going to talk about 4 other types of pointer errors that can all mess up the heap and really cause you grief. So a memory leak's bad enough. You can run out of memory if you run your program for a long time. I would say the corrupting your heap is worse. So how many ways can we corrupt a heap? Well, what we can do is use a freed block. So we call free, we give free the correct memory address, and then we go and keep using that block. And so if you go back to the previous page and look at the chunk diagram for a freed chunk, there's forward and backward pointers in there. There's information about the previous chunk status. So if your program's overwriting that information, you're corrupting linked lists, and you can cause all kinds of havoc. Number 3, you could free an invalid pointer. So you call free, you give it a memory address which is not a memory address that was returned by malloc. So when when free gets an address back, it assumes that it is pointing to the correct position in a chunk, and then it will look backwards to find the size of that chunk and information about previous chunks and that kind of stuff. So if you give it an invalid pointer, then it's going to be interpreting memory contents as information that it really isn't. So that would be bad. Number 4, you could double free a pointer. So the first time that you free it, it's a valid pointer and everything's fine, but then you accidentally free that again. Maybe using some kind of loop structure or something. That's really the same as number 3 here, if you think about it. And last one that I've got here is something that's pretty easy to do, is that you request a block of a certain size and you write past the end of it, which means that you're now writing into the next chunk that's beside it in memory. Or if you, so that's overflowing, you can also underflow, write to lower addresses than the start of your chunk. So you can over or underflow a block. And so these are all examples of corrupting the heap. So there is a tool out there called Valgrind. And the first time I heard somebody pronounce this, I thought they were reading it wrong, but it turns out that this is a term from Norse mythology, and it is indeed pronounced Valgrind. And this is a memory misuse checker. So you compile your program and use the flag to say to insert debugging symbols, and then Valgrind will run your program and it will detect things like memory leaks and corrupting the heap. And it's quite configurable. It's pretty easy to use, really, and very useful. Yeah, so it's a great free tool, and so I'd recommend you to be aware of it if you're going to be doing systems programming. So that's it for dynamic memory. Now we're going to move on and talk about static memory allocation.